Here are some examples for IMF Practice 1. How about we start on number 1? We have O3, O, 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 and we have valence electrons of then 6 3 times, so we get 18 electrons. Well, I got to use 4 of them there for sure for bonds. So that's 4, 6, 8, 10, 12, 14, 16, 18. How about that? So that looks pretty good at first, but the middle one Venn diagrams like this as a 6 valence electron count, and it's not going to stand there and take it. It's going to get grabby, but the choices to get grabby from are equal. And as I say, when the choices to choose from are equal, it chooses equally. So it's going to get half a double bond both directions. So I'll pick the right side just because I feel like it today, and I'll make a double bond in here. It takes that pair and puts them in here. So that's a double. And I drew a line here, but now that I'm done, because this is now 2, 4, 6, 8 on the middle, maybe just to be helpful, I'll draw that as a cloud with 2 dots. But either way, you will get the same answers. And so this so far is still repeats from our previous stuff about Lewis dot diagrams. And what shape is that? I have 2 bonded atoms and 1 unshared cloud on the center point. So that is bent. So we'll put bent. And what else do we need? Do we need brackets? No, because it's not plus or minus in the formula. It is a resonance structure though, isn't it? Because it borrowed equally in multiple directions. Resonance structure. And is it an octet violation? No, it's not after I finish the resonance structure part. Okay, so that's all the old stuff. Now, is this polar? Well, what we're going to do is get our electronegativity chart and check the differences between the bonded atoms, but they're all oxygens, so you don't even really have to look, but let's just pretend. And we get 3.5 minus 3.5, because this is a 3.5 and that's a 3.5, so the difference between the bonded atoms, of course, is 0. And of course, we get the same thing here. And if you don't have polar bonds, if you don't have a difference of 0.5 or greater, then you don't have a polar molecule. And maybe you hit pause and copy this set down right here. Also, I forgot the word difference here. So 0.5 difference equal to or less than is a polar bond. So equal to or greater than 0.5 of a difference is a polar bond. But if you don't have a polar bond, you can't have a polar molecule. So this one is nonpolar. And we don't have a polarity arrow because it's nonpolar. What intermolecular forces does it have? Let's go to our chart here that we wrote out from strongest to weakest. And the first time that you reach a yes answer, that's the one you put down, the strongest one that you can find. Is O3 ionic? Is it plus or minus in the formula? No. Does it have hydrogen bonding? It doesn't even have hydrogen. Is it polar? So it's dipole-dipole? No, we said it's nonpolar. So we get no, no, no. So we just put the weakest one. Everything has London dispersion forces. Everything can have that. So is that the strongest one? Well, this time it is. But it's the weakest. Yeah, but it's the strongest one that this one has. So we will put London dispersion forces as its strongest intermolecular force. How about number 2? NH. Now we will discover, I think, that those H's really aren't spread out equally to the side, but maybe you put them there because you didn't see that coming, and that's okay. I'll put them there just to prove that it doesn't really matter. And this isn't art class, so I won't argue about the exact shape that it's drawn in. Now, how many valence electrons do we get? 1 and 1 and 5. But this minus sign means I get an extra 1. So how about we count the nitrogen as a 6 instead of 5? So I get 1 and 1 and 6, so I have 8. So I know I will need 2 bonds at least. So how about we use 2 and 2 there? That's 4 used up. We said we get 8 total, so that is 4 left. Now the classic mistake would be to do this. But hydrogen just can't have 4. That would be definitely wrong. So we will put them on the N, who wants them anyway. So something like that. Or some people put one up and one down. I don't want to argue about that. My point is, when you look at the molecular geometry chart, do you know the shape it is? 2 bonds and 2 clouds is bent. Oh, we should double check all our little notes. Does this need brackets because it's plus or minus? Yes, it's minus. Is it a resonance structure? No. Is it an octet violation? No. So we'll leave those off. Okay, back to the polarity stuff. What's the polarity difference between H and N? This is a 3.0, that's a 2.1. Maybe you write those down. I don't know, you don't have to. I will just to show what I'm doing. Is the difference between them 0.5 equal to 0.5 or greater? Yes. Is that a polar bond? Yes. These bonds will shift toward the stronger number. You don't have to draw these arrows. I'm going to just because I think it's helpful. Most people end up skipping them. But these bonds, like that Miss Kendall in the video showed us, are moving in toward the N. Or to be more accurate, they're moving this way toward the N, which makes these clouds get bigger as they run away from these electrons that are moving up. So are they polar bonds? Yes. So could this be polar? Could be. Here's the next question. Does this have a dipole moment? And we need a dipole. And I will write this down. It needs a dipole to be polar. Maybe make a better D there. Which means it needs a plus side and a minus side. Maybe you need to hit pause and write that in. So can I find a plus side and a minus side of this? We said these are the H's, and these bonds are getting pulled up. So these are becoming a partial plus, and this side is getting more than its normal share of electrons. So this side is going to be minus, and this side is going to be plus. So I know that my H's are kind of at the wrong angles, but how about we just say cloud side and opposite cloud side? We said the cloud side is going to be partially minus, and the opposite side is going to be partially plus. You don't actually have to write those if you don't want, but if it helps, that's great. I won't count it off either way. And this, again, is delta. It's lowercase delta. And maybe you learned in science back in middle school that triangle is a Greek letter called delta, and it means change. So this, it turns out, is lowercase delta. And for people thinking that doesn't match at all, I know, but in English, sometimes we don't match either, right? So this means change, and this means like a little bit of change. So this changed a little bit to plus, and this changed a little bit to minus, at least somewhat. So can I draw a line through the middle of the real shape that shows a minus side and a plus side? I can do that, huh? You don't actually have to draw the line. If you can just imagine it, that's great. This side would be plus, that side would be minus. And I do have a dipole because I have a plus side and a minus side separate from each other. So is it polar? Yes. Toward the clouds or away from it? Toward the clouds, we said, because that's the negative side. We're going to draw the arrow toward the negative side. Maybe hit pause and write that down. The polarity arrow goes toward the negative side. And maybe another note is I did not say that it always goes toward the clouds. Sometimes it goes away from the clouds. What it goes toward is the negative side. And I don't mean this negative, I mean this, that this is the negative side. In fact, you know what? How about we do this just so it doesn't look like I'm pointing at that negative? How about we put it on this side? But it's still headed the same direction. So this is the negative side, and this little plus back here means that this is the plus side, away from the clouds. How about we do PF3? P, F, 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 and I'm going to speed up a little bit here. Fluorine, you might remember, is a 7 valence, or go check your chart. I'm going to speed up. Phosphorus is a 5. Go check your periodic table if you forget. And I'm going to use 1 to make a bond, 2, 3. And I said I get 5, so I have 2 left over, and I'm going to put them up here just because they got to go somewhere on phosphorus, but you could put them down here or something. Do I need brackets? No, it's not plus or minus. Did I change anything around to make equal sharing somewhere so it's a resonance structure? No, I didn't. Is this an octet violation? 2, 4, 6, 8, 2, 4, 6, 8. No, everybody's happy at 8. Okay, so it's not an octet violation. All right, so what shape is that? How many bonds and how many clouds? 3 bonds and 1 cloud. 3 bonds and 1 cloud would mean it is trigonal pyramidal. So how about we abbreviate that for time and space? So is this polar? Well, what's the difference between phosphorus and fluorine on our electronegativity chart? 2.1 versus 4.0. Ouch, that's a lot. Is that equal to or greater than 0.5? Yeah, it's a lot more. So are these polar bonds? You betcha. Toward what? Toward the strong number, which this time was the fluorine, toward the strong or bigger number. So these are all moving out from the center this time. You don't have to draw the arrows, but you can. If in case you think that helps, it's fine. And they all moved outward, but did they move equally in space? And the answer would be no, because this is the shape we're really dealing with. And so in this sense, they all moved downward. Or if you turn it around, fine, they all moved upward. But my point is they did not move equally in space in all directions. So if these moved this way, and this way, and this way, then this would be, let's turn it around, that's weird that way. This would be the positive side, and this would be the negative side because the electrons are moving toward the fluorines. So is it a polar bond? It's very polar bond. Is it symmetrical? No, because I can draw a line through the middle that makes a plus side and yet at the same time a negative side. So is it a polar molecule? Yes. Which way? And I want to point this out. I picked this one on purpose. This time the arrow will be away from the cloud. So the arrow does not go to or away from the cloud. The cloud is not the point. The point for the arrow is toward the negative side. And this time, because these F's are very electronegative, the negative side will be away from the cloud. So I know that I drew my F's kind of in a dumb place and it looks like they're spread around equally, but we know that really it's this. And the arrow needs to go at least away from the cloud. I am not saying you need to go draw this F down and this F down. We can leave it like that. It's not art class. And if you want to leave it like this, I can live with it. But the arrow, the polarity arrow, needs to go away from the cloud this time. And that is the positive side. The cloud side is the positive side. What kind of intermolecular forces do we have? We go in order. Is PF3 plus or minus? No. Does it have hydrogen bonding? It doesn't even have any hydrogen. Is it dipole-dipole because it is polar? Yes, it very much is polar. It's quite polar, we just said, because the difference was so high. It's very polar, and so that's our strongest IMF, and so we're going to put dipole, dipole, except I'm tired of writing it and it doesn't fit, so I'm going to put dip, dip. And that's going to be my final answer for that one.